let's try to make that concrete by applying this again to the whole angle data. Notice that since I've decided that electrical discharge machining process turns out reasonably normally distributed observations, I've already got methods that work here, but as a contrast, let's think about what these methods, this more general method offers in this problem. Once again, those data in table 5.7, and go back to 5.7 and find that the smallest observation in that table, if I look through it, is 42.017 degrees, and the largest value in that table, if I look through the table, is 46.050 degrees. And what I'm talking about here then is making an interval that runs from 42.017 up to 46.050, and using that either as a prediction interval for one more observation or as a tolerance interval for, say, some fraction, say 95% of all future whole angles. Well, as a prediction interval, this has associated confidence that has nothing to do with the specific numbers that are the two endpoints of this interval. It has only to do with the sample size, and that is 50 minus 1 over 50 plus 1. That turns out to be 96.1. That is 96.1%, 0.961 if I want to speak of it in fractional terms. That is, I can be 96% sure in using minimum to maximum of 50 of catching a 51st whole angle. As a tolerance interval and just pulling a figure out of for an example here, a tolerance interval for a fraction, say 95% of all future outcomes, I have associated confidence. Well, that again doesn't depend upon the exact values that I have for the minimum and maximum in the sample. It only depends on the sample size and the p that I'm interested in. And so what I do is take 1 minus 0.95, the fraction of the population that I'm trying to capture, raise it to the sample size power, take the sample size times 1 minus p, so that's 0.05, times p, which is 0.95, and raise it to the sample size minus 1 power, and that's 72.1% or 0.721. That is, I am about 72% sure of capturing 95% of a population using the smallest and largest of the of a sample of size 50.